Hi everyone. So in this video we're going to be talking about non-homogeneous second-order linear constant coefficient differential equations. And the key word here is this is non-homogeneous. So that's the big difference between what we've done and what we're doing now. This is pretty much a three-step process. We can say that our general solution in this case, y is going to be equal to yc plus yp. This piece here, yc, is what we're going to solve for first. So yc is the what we'll call the complementary the corresponding homogeneous solution. So what I mean by that is we just pretend that this is homogeneous. So we set g of t equal to 0, solve for it. We saw how to do that in the last video. And that'll be our y of c. So yc is going to look like c1y1 plus c2y2. Second step is we're going to use g of t to solve for the particular solution. And then the last step, again, is just going to be setting our general solution equal to yc plus yp. I'm writing this down as one step, but this is sometimes a lengthy process. So I am going to start off with an example to kind of show you what this can look like. So let's say so find the general solution of y double prime minus y prime minus 2y is equal to 8e to the 3t. So it's definitely non-homogeneous. First thing that we want to do is find the corresponding complementary solution. So yc, that's going to be equal to, we're going to temporarily turn this into a homogeneous differential equation. We know how to do this, right? Assume y is equal to e to the lambda t. That gives us lambda squared minus lambda minus 2 is equal to 0. And I think we can factor this one. So this is minus 2 plus 1. So we get that lambda 1 is equal to 2, and lambda 2 is equal to negative 1. So my complementary solution, yc, is going to be equal to c1 times e to the 2t plus c2 times e to the negative t. And that's it for yc. Yp, like I said, we're going to be using g of t to solve for this. Excuse me. Specifically, we're going to first off guess the form. Of the particular solution based on our g of t. So our g of t, and I'm going to have a whole video about guessing the form on this because there's a lot of things that we need to consider for this. But this example that I've given is fairly easy. So in this case, we have g of t is equal to 8e to the 3t. So I'm going to say that the form of my particular solution, I'm just going to guess that it's going to look like that. So the process is a little bit more complicated than this. Like I said, I'll have a whole video about how to get this form right, so you don't have to guess. You'll just be able to figure out the correct form. But let's just assume that we know that y of p is equal to a e to the 3t, some constant times e to the 3t. So I do have a second order differential equation here. So the idea is that any solution should be able to be plugged into that differential equation, and we should end up with something like 0 equals 0, or showing that it's a valid solution. So I'm going to try plugging in my yp, y prime p, and y double prime of p. I'm just going to try plugging that into my solution here, or my differential equation rather. So the original differential equation was y double prime. I'm just going to write my p's down here, minus y prime of p minus 2y of p is equal to, and in this case I am going to include that. G of t in there. So if I plug everything in, I end up with 9a e to the 3t minus 3a e to the 3t minus, it looks like 2a e to the 3t, and that's all equal to 8e to the 3t. A lot of simplification we can do here. So I can see already that dividing by e to the 3t is something I can do with all these terms. And so that'll give me 9a minus 3a minus 2a is equal to 8. And that means I can solve for a. So that means, let's see, 9 minus 5, so 4a is going to be equal to 8. So a is equal to 2. That a was originally from my particular solution, so yp is going to be equal to 2 times e to the 3t, since that was my form. Something that I'd like you to note here, so the next step is just saying this, y to the yc plus yp. So we get that y is equal to c1 e to the positive 2t plus c2 e to the t plus my particular solution 2 e to the 3t. So what I wanted to point out about this was notice that we didn't have any points in here. We didn't have any y naught is equal to y of t naught or anything like that. So we can't solve for C1 and C2, but we didn't need that to solve for A. So these coefficients here, you don't need any points to solve for them. You can actually use this process where you plug in y double prime and y prime of p. If you plug that into the differential equation, you can solve for A without any additional points. So just getting the form right can sometimes be a process, right? So figuring out what the form of the particular solution is, but you do still need to solve for those A, and then later we'll have A, B, and C that you'll need to solve for. But for this problem, this is our general solution. And so that completes the problem. In the next video, I'm going to talk about some of the ways that this can become a more difficult problem, or choosing the form of the particular solution isn't as easy. So we'll see that in the next video.